Hi, welcome to this organic chemistry quick video. This is going to be over carbohydrates, and mind you, this is a very brief introduction into the idea of carbohydrates, something that you will cover in much greater detail in biochemistry. So starting off, what are carbohydrates? The technical definition is polyhydroxyaldehydes and ketones and things that hydrolyze to form polyhydroxyaldehydes and ketones. That might sound like a really scary definition, but these are actually words that you hopefully can kind of figure out what's going on with them. First, polyhydroxy. Poly means many, hydroxy means OH groups, so this is a lot of OH groups. Aldehydes and ketones, those are just the functional groups that we've already learned, hopefully first semester. Aldehyde is a double bonded O at the end of a chain. Ketone is a double bonded O in the middle of the chain. And things that hydrolyze, so hydro, water, lyse, cut, so cut with water to form polyhydroxyaldehydes and ketones. One of the big tricks to carbohydrates is you have to have at least 3 carbons, okay? So in order to be considered carbohydrate, you have to have 3. And the chemical formula, the general chemical formula for carbohydrates is CnH2OM. Okay, so N and M can be different numbers, and that is the general formula for carbohydrates, which is carbo, carbon, hydrate, water. A little bit more information. Like I said, they can be aldehydes or ketones. If they're aldehyde carbohydrates, we call them aldoses. Ose is a sugar. If it's a ketone carbohydrate, we call it a ketose or a ketone sugar. They both have the same chemical formula, however, they're going to differ in the number of chiral centers. And this is because, see if I can get the top to go back away. No, come back. Is because on ketones, the middle carbon could have the double bonded O, which would be 0 chiral centers. On an aldose, you're always going to have at least 1 chiral center. We also have these terms called stereoisomer, well, it's called triose, tetrose, pentose, hexose. This is telling you how many carbons you have. So a triose is going to have 3 carbons, a tetrose will have 4 carbons, pentose 5 carbons, hexose 6 carbons, and we have these grouped as stereoisomers. And that, for more information on that, you really need to go to the long video. And here, that's kind of about all I really want to cover. All right, we usually draw our carbohydrates in Fisher projection. This is actually why Fisher projection was kind of developed, to make it easier to draw our carbohydrates and our amino acids. With Fisher projection, you put the aldehyde or ketone group on the top. The arms are coming out to hug you, so the OH and H's are coming out to hug you. And we have LD designation, okay? This makes nomenclature really nice. You look at the bottom OH group. If it's on the left, it's L. If it's on the right, it's D. So these are 1, 2, 3, 4, 5, 6. These are hexoses. The first one is an aldose hexose, and it is a D-aldose hexose. The one on the right is a D-hexose ketose. There we go. More chiral centers means that you have more stereoisomers. So if you have n number of chiral centers, there are 2 to the n power of stereoisomers. Again, on the longer video, there's a whole chart that has a bunch of them on there, but that's about all we want to go through. Now we're going to move into the carbohydrate reactions. First one is epimerization. So epimers are 2 compounds that differ only at 1 chiral center. You can make epimers with our carbohydrates by using sodium hydroxide in water. First thing that'll happen with sodium hydroxide and you got an alcohol, you're going to have an elimination reaction. Then because we've got water, you can have an addition reaction. And the result of that is going to give us a epimer where our OH can end up on either the right or the left-hand side on that very top carbon. Next reaction is going to be a reduction. If you've got sodium hydrate, did I skip one? Nope, I didn't. All right, if I've got sodium borohydrate, I can reduce my aldehyde down into an alcohol. So we call it an aldehyde. All right, essentially you're adding 2 hydrogens across your C double bonded O. And this sounds slightly familiar, maybe like when we hydrogenate with hydrogen on a metal. Yep, it's the exact same reaction. We're just doing it with NaBH4 on the last one. So you could do the same type of reaction using just straight up hydrogen on a metal. You can also oxidize, okay? Oxidizing often means that you're adding in an oxygen, and that's exactly what we're doing here. If you have bromine and water, you can add a oxygen well, you're actually adding in a full OH group and plucking off the hydrogen, but you go from an aldose to a carboxylic acid, and those are called aldonic acids. Same type of a reaction here. You can also use HNO3 and water with heat in order to form a carboxylic acid. This will not only react on your aldehyde, but it'll also react on your terminal alcohol. Okay, only on the terminal alcohol, won't happen on the other alcohols. Come on. All right, you can also lengthen your chain by using something called the Keelaney-Fisher synthesis. First thing that you do is you're going to have an addition of HCN across your double bond, so cyanide and then hydrogen. Two of those will come together in order to, good golly, let's see. Two of them will come together and you'll end up with a aldehyde on your end chain. It can either end up on the right-hand side or the left-hand side. That's why there's two of them showing, because you're forming a chiral center. It's not going to be stereospecific, so you'll end up with both the R and the S up there. You can also use hydroxyamine and then ACO with sodium methoxide to shorten your chain. So the last one was lengthening the chain, now we're shortening the chain. So if you see NH2OH and then AC2O and then methoxide, it could be sodium methoxide or just methoxide, you're going to just be chopping off the chain. And on the next picture, it's the same type of an idea. This one's just called the rough degradation. The last one was the wall degradation. This is just a different set of reagents. What you're really doing is cutting off the aldehyde, and then the next alcohol group is becoming the OH. But when I'm looking at these, it's a lot easier for me to just pluck out the top line. You're shortening your chain by 1 carbon. And that is all that I've got for you guys as far as carbohydrate reactions. In class, we'll talk a little bit more about an introduction to biochemistry and carbohydrates, what they are and different types. But that's all I got for you guys today. Have fun!